Okay, this is talking about geothermal heat pump systems, and this picture here basically shows a machine that is basically capable of drilling in the ground. Utilizing this type of technology obviously has some environmental positives. It is expensive. It requires a lot of work. It requires a lot of land preparation. I would probably say I've never seen this physically done here in any areas here in Southern California that I'm aware of, but this is proven technology. Some of the various pictures that you'll see on this one here is on page 1348, your textbook, figure 44.1. This is a diagonal drilling rig showing a small bore drilling equipment. Here we have a different machine. This is figure 44.42. It's diagonal drilling rig showing the resonance and a small bore drill. So a lot of machinery involved, and I'm sure there's some cost involved with this. Okay, in this particular arrangement here, we have a, this is figure 44.47 found on page 1349 of your textbook. This is a diagonal earth loop supply, liquid and return vapor manifolds in a pit. Here we have a gentleman that is appears to be excavating this area in order to, and this is found on page 1346. This is a trencher digging up a trench for refrigerant loops. So you have to rent machinery in order to do this. And once again, you need to have the land available to do this. You know, one thing is, depending on what part of the country and you might have to have special permits. I really am not the expert on this to let you know what is done on this. Okay, here in figure 44.36, a copper header is being brazed to the supply and return loops by a technician. And so obviously we're utilizing copper, but the copper inside the ground has no loop, has no joints. So all your copper loops are going to be seamless in one piece. You will not have joints in the ground, in the burial of this type of copper. Okay, this appears to be a water box. In this particular case, it's a header box being positioned over the copper header. So basically you would install like a sprinkler box over these brazed joints in order to gain access to it in the event that you have issues with this loop system. Okay, you have an interesting situation here. I'm kind of, let me see if I can find a picture of that, because that definitely looks like a copper tubing that has been compromised in some way, shape, or form. And I'm not really sure what the purpose of that particular illustration is involved here. Please let me look this up and I will tell you what that is. Okay, I found it. It is on page 1327, and this is figure 44.2, and it says here, notice the shape of the inner tube. This increases the surface area, increases the rate of heat transfer. So basically, utilizing this type of copper loop piping, basically we want to maximize heat transfer through this pipe. Okay, in the same figure 44.2 on page 1327, a cutaway of the coaxial cable, which we talked about in the slide presentation. This is basically a tube within a tube heat exchanger. The refrigerant flows in the outer tube while the water flows on the inner tube. So basically what we're doing here is we are creating what we call a counterflow refrigeration effect. In other words, We're going to maximize heat transfer because refrigerant flows one way, the water flows the other way. The ideal beauty of this whole idea is it maximizes heat transfer. Okay, in this picture here, which I believe I saw a little earlier, basically it looks like that spider connection that we looked at previously. And I believe, hold on a second, see if I can find that particular picture. I believe that picture is located on page 1348, and this would be 44.46. This has the manifold details and a diagonal earth loop system in this particular case. There's many different technologies here. Okay, here we have the heat pump here, one form of it. And notice that you have a heat pump, you have your hose connections, you have the ground loop down below, and it's very environmentally friendly as far as the makeup of this thing. And this particular illustration is located on page 1335 of your textbook under 44.18. Schematic showing the purging unit hooked up to the heat pump for power flushing air and debris from the ground loop. So when you commission these systems, you have to purge them. You have to make sure they're free of air prior to putting these things in service. Okay, here, this is inside a mechanical room. This is found on page 1339 of your textbook, figure 44.25, a water-to-water heat pump installed as part of the hydronic heating system. Okay, here we have the trencher in progress, digging. This is found on page 1343, figure 44.30. So we're utilizing polyethylene plastic coated pipe being ready for buried in a trench. Once again, you need to have the land in order to make this thing work. Now here we have a bunch of different loops. We talked about this in the slide presentation, and I believe in your textbook there is an explanation on these different types, the advantages and disadvantages. And just give me 1 second here. Okay, you're going to find these on page 1334, figure 44.7, different flow paths in ground loops. So these are just the different flow paths for the ground loops that are installed in the ground. Okay, there's a basic well, like you would find. Okay, so this would be figure 44.19, basic well, drilled well, basically shows the well cap, the electric line for the submersible pump. You got the water line down below it. Then you got the pitless adapter. You have your drop pipe, your static water level, well casing, submersible water pump, well screen. Now, the main thing you got to look at if you're going to utilize well water is the mineral content of the water. The mineral content of the water is high. You are going to have problems with the heat exchangers becoming calcified and insulated due to mineral buildup. So you got to be aware of this. Now, if this water is used for drinking and for a ground loop heat pump system, there has to be a separation, because if there isn't, what is going to happen is if you add any chemicals, obviously this will affect your water supply. So there's some careful considerations that need to take place when utilizing a well. Okay, here we have a situation. They show a area that is filled with gravel. This is found on page 44.23. This is a dry well. So what's happening is this well has been utilized in some time in the previous whatever, and now it's filled with gravel. And basically we are rejecting discharge water from an open loop heat pump system into this dry well. The theory behind this is we can recharge the aquifer because the water is going to collect around the gravel, and that in turn is going to hopefully allow minerals to take and either pick up or be released into the rock formation. And of course, this water will find its way down to the water table. We talked about this previously, but this is figure 44.24, operation of a well water pressure tank. And this can be found on page 1339. Here we have another illustration. Notice that we have a what appears to be a refrigeration system adapted for, in this case, a geothermal. So basically you have the regular components, which consist of the compressor, the evaporator, the condenser, and the metering device. What changes here in this particular picture, and this is found on page 1339 of your textbook. This is the heat exchanger configuration on a water-to-water heat pump system. So we're utilizing water for the earth loop as well as for the load going to for the condenser. Okay, in this illustration here, we have a buffer tank, and this is found on page 1341. These are the piping connections between the heat pump, the buffer tank, and the buffer tank and the heating circuits. Excuse me, they're not shown on this illustration. This is on page 1340. So the buffer tank location on a water-to-water heat pump system. Now this is figure 44.28 on page 1341. Now we are showing the heating circuits that are involved. So you can see you have different loops here for the distribution system. So basically, these would represent the individual loads here inside a structure, okay? And of course, you got the buffer tank, and then of course, you've got your heat pump system and your earth heat exchanger. Now, what goes on with this piping here? Okay, basically in this type of piping, which is found on page 1345, two small vents or grooves allowing the pipe to act as a vented double wall heat exchanger. The inner part of this is copper tubing for refrigerant. And then of course the polyethylene surrounds this copper tubing. And then we have the vents in this polyethylene plastic coating. And I believe this is to allow for expansion, contraction, remove moisture, that kind of thing. And this would be considered direct burial, if I'm not mistaken. But remember, no joints in the ground. Okay, here we have the dedicated geothermal well. We're not utilizing this well for domestic water consumption in this case here. It compares to the previous picture we saw on the well, except there's a few little changes here showing what's going on inside that well. Okay, I'm trying to find that picture so we can talk about this in more detail. Okay, so this one here would be, okay, let's see here. I'm looking for the dedicated one. I have the one for the basic, which we already previously covered. Okay, here we go. I'm sorry. This is on page 1338. This is figure 44.22. And basically, we have, of course, the electric line for the submersible pump, the return line, the supply line, submersible pump, which is plugged into the power source, the static level indicator where we want the water level to remain, and the well casing is obviously required here. The soil is what they call unconsolidated, loose, unpacked. You have rock consolidated, uncased. It terminates the return line 2 or 3 feet from the bottom. So basically, we want that return line far enough down so that we don't have a situation where we're pumping water from this dedicated well for the heat pump system to go dry. If it goes dry, basically you're going to pump air non-condensables in there, and you're going to foul the system and not create the heat exchange that you're trying to achieve here. Now, from my first take of this illustration, it looks like a piece of art in a park, but I can assure you that is not the case. There is a reason for this picture, which I will talk about in just a minute. But basically, this, once again, is not a work of art. This is actually part of the geothermal process. I'm kind of curious to see what your textbook has to say about this illustration here. Okay, this is figure B, found on page 1330 of your workbook. And this is a prefabricated Slinky ground loop waiting to be transported to the job site. So it looks like this comes shipped in this form, and you have to untangle this mess. Have a good day. That would be a little hard to do. Okay, here's those Slinky units, which are being installed. This is found on page 1331. And the 4 Slinky ground loops and freshly excavated trench waiting to be rolled out. Okay, here we have the technician working on the supply and return headers for the Slinky groundwater loops, which enter the basement of the house. Now, one thing that you have to do when you're installing this, you have to waterproof these fittings, because now think about it. Since this is in the earth, which will be, I'm assume, packed, and once the loops are put in with this Slinky heat exchange system, water which goes through the soil could end up weeping through these holes. So I imagine there must be a process that has to be in to prevent water leakage from the ground into the basement where these piping units come out. Okay, in this situation here, this is letter D. Basically, this would be, he's in the process of rolling out these Slinky groundwater loops. In this picture here, the technician is rolling out the last of the 4 Slinky ground loops here. So you can see how they look like Slinkies now laid down flat. Quite interesting. But look at all the earth that has to be moved in order for this to be put in. It's an expensive process, I can tell. Okay, and in this illustration, 44.12, the freshly excavated trench showing 4 Slinky ground loops with a large backhoe in the background. Okay, here we have the different types of ground loops for this geothermal heat system. You have a diagonal, you have a vertical, and you have a horizontal. So basically, these are the 3 types that you are going to be normally dealing with if you put in this type of a ground loop system. And once again, from an environmental standpoint, it's pretty much a foolproof process. It's not a cheap process. It involves a lot of work, a lot of trenching, a lot of backhoe work, and your first costs are very high. But that being said, after this is installed, you have a very good system. This, by the way, is found on page 1347 of your textbook, and this is figure 44.38. Once again, we are illustrating the diagonal, the vertical, and the horizontal earth loop configurations for this house. Okay, here we have what appears to be an air handler. And this is figure 44.48. This is the compressor unit, earth loop, and air handler. So basically, it's your condensing unit, air handler, and then, of course, the earth loop piping that makes this whole thing work. Okay, in this situation here, this is on page 1348 under 44.44. This is the horizontal earth loop installation. And notice how the loops are in a horizontal rather than a vertical or a inverted position. Okay, these guys here, I can assure you're not Caltrans workers. They are doing what they call diagonal drilling rig with the workers feeding copper earth loop into a small bored hole. Now, remember, when you're feeding this type of tubing in here, no joints in the ground. All the joint connections are made above ground, and they usually have a box where you have access to in case we have to fix them. Okay, this illustration here, we obviously have, this is a rig. This is figure 44.40, which is found on page 1347, diagonal drilling rig near a residence. Okay, in this illustration, 44.40, diagonal drilling, showing how it's done near the structure. Okay, in this illustration over here, this shows how the earth loops, in this case here, this shows how these heat pumps work in the heating mode and in the cooling mode. I would like to refer to the page where this can be found in your textbook, so we can explain this in more detail. But notice that the heat is being transferred from the water to the refrigerant. And if you look at the flow, basically you're going to have a counterflow situation here. Remember, counterflow is employed in order to maximize heat transfer between the two components. It's a proven process. We use this a lot in commercial air conditioning refrigeration systems, and works extremely well. And I believe we're getting close. Here we go. This is on page 1326. This is an open loop water source heat pump in the heating and cooling mode. So we're utilizing an open loop water source heat pump. So basically, you have the compressor down here. We have the fan coil and the evaporator. You have the metering device. And then, of course, we have the condenser coil utilizing water in order to take and remove the heat from the refrigerant. So basically, you have a refrigerant in here. Notice that we're not using the four-way valve in this case. Then we go over here in the cooling mode. The only major change that you're going to see here, heat is being transferred from the refrigerant to the water in this case. So basically, we're either transferring we're transferring heat from the water to the refrigerant or from the refrigerant to the water, depending on if it's heating or cooling. Okay, in this illustration here, we show a gigantic loop here, and I believe this is found on page 1330 of your textbook, and this would be figure, appears to be figure 44.10 at the left-hand bottom. It says, in this case, heat being rejected from the ground loop to the surrounding earth. Notice that the soil depth is anywhere from 4 to 6 feet. In this particular illustration, also found on page 1330, this is a single layer horizontal ground loop in the heating mode. In this illustration, which is right directly above on the same page, this is heat, which is came from the house, is being rejected from the circulating fluid into the ground loop, in this case, into the ground. And here we have a situation, we're looking at this Kubernetes type pipe. You got a steel shell and you got water. So basically this Kubernetes is a great material, resists corrosion. It does resist some chemical, how do I say it? I won't say that this is not capable of being scaled, that can get full of water scale, because it can. But this type of piping, or I should say the metal that is used in this second of this tubing, is very, very good. Works very well, lasts a long time, and if it's installed correctly, you should get many years of good service. And I'm trying to find, there we go. This is on page 1329 of your textbook. And basically this is a ground loop showing a, okay, hold on. This is figure 44.5. And this is the cross section of a counterflow coaxial heat exchanger showing the leads or extended surfaces. So basically you have the water flowing one direction, refrigerant flowing the other direction. And this is a direct burial type application. Now here's something I used to work on a lot. This would be an example, and this is found on page 1329. And this basically is a coiled coaxial heat tube within a tube heat exchanger. The tubes are sealed in such a manner that the inside tube is separated from the outside tube. And basically you're going to circulate refrigerant one direction, water in the other. So basically what we're doing here again is we're utilizing a water source in order to remove the heat from the refrigerant. This was done a lot on commercial refrigeration years ago, but due to the scarcity, non-availability of water in a lot of remote areas, this, by the way, has an excellent heat extraction ratio. Water is far superior to air. The problem is water is in short supply. And the other problem is water tends to scale up these coaxial heat exchangers. And over time, you have to take and clean the scale out utilizing harsh chemicals such as muriatic acid compound, which obviously, if you don't take the proper health precautions, can damage your skin and other things. Okay, here we have a picture of the United States and page 1328. It shows the temperature of wells ranging from 50 to 100 feet, 50 feet to 150 feet deep. So if you go here in good old Montana, 50 degrees here, 48 degrees here. Let's go to North Dakota. Notice that the water temperatures are lower in North Dakota. Don't ask me why. That's where my family's originally from, and it's very interesting. Way up here into Canada, which I believe is Saskatchewan up here, it's 44. So the water is very cold coming out of the ground from the well here, up in the other upper portion of the United States. Now, if you come all the way down here to Florida, 74 degrees, well, that's not very cold. New Mexico, 54 degrees, that's interesting. I don't see anything here in Arizona. Maybe that state's too warm. I have no clue. If you get up in the Puget Sound, Port Orchard, Bremerton area, it appears to be 52 degrees. So I would say your temperatures are much colder in the Midwest than they are on the Pacific coast. And they're also very cold up in the state of Maine. Okay, this we talked about previously in the PowerPoint presentation, but in order, and let me refer you to the page number where there's more information in your textbook that you can read about. But notice that we're utilizing a cooling tower here. We are also using a boiler in order to take and mix the water temperature so that we get the correct temperature going through. So in some cases, the water is so cold, we have to add some heat because otherwise it interferes with the process of making this thing work. Okay, this is found on page 1327 of your textbook. This would be 44.3. This is an open loop water source heat pump with boiler and cooling tower to maintain the loop temperature. Okay, we have an interesting illustration over here on this page. Notice this appears to look like an accumulator, but I don't think it is in this particular case. Let me find out. This is found on page 133, 44.16. This is a domestic hot water loop showing the counterflow coaxial heat exchange. The water is heated by the refrigerant loop. So basically, this is a domestic hot water heater. Here we have a counterflow coaxial heat exchanger. The heat pump compressor, superheated refrigerant goes through here, cooler gas comes out. So basically, we're using the waste heat off of the heat pump or air conditioning unit in order to create a heat source to heat this water up. So basically, this is going to assist with reducing using a fossil fuel such as natural gas or something in order to heat hot water for domestic use by utilizing the compressor. Now, the problem is this compressor doesn't run continuously. You could have periods where the hot water is hot and periods where the water is not so hot, unless this tank is very well insulated and you have sufficient hot water volume inside this tank in order for the drawdown to work. So if you're taking a Hollywood shower, which is a long version of a Navy shower, no, it isn't. It basically, if you're taking a long shower in your house utilizing this concept, you will deplete the water here very quickly. And natural gas, of course, has the ability to heat the water very quickly. Whereas if you're using waste heat from the compressor, it's a continuous heat source as long as the compressor is running. If it's not running all the time, you might have problems. Okay, here this looks like a condensing unit. You can obviously see the compressor over to your left, and you see the other parts of this refrigeration heat pump system. Notice that it's very compact. It's not that hard to work on. This is found on page 1349 of your textbook. And this is figure 44.49, the internals of a heat pump compressor showing the active charge control with 2 sight glasses. So the sight glasses, kind of curious, where are those? Oh, there they are right there. So we can actually see how much refrigerant is inside the system here, high and low. What's interesting, we utilize the same concept with receivers on Amtrak railroad passenger cars. You have your upper limit and your lower limit. Very interesting. So basically, depending on the load, it'll determine how much refrigerant is being used in the system. Okay, here we have the situation on page 1348, and this would be figure 44.45. Shows the earth loop manifold right here. So basically, notice that you got your piping come in, and then you got what you call your spider works right here. Notice all your connections are made in a vault type arrangement where they're accessible in the event that we have leaks. These are your earth loops that are direct burial. And then of course, this is your line sets that go to the heat pump unit. Okay, this appears to be a standard air conditioning system with a modification. So if you look over onto the right, that appears to be an outdoor condensing unit. And this will be found on page 1344. This would be figure 44.31. This is a retrofitted system utilizing the refrigerant management module. So we're using a standard condensing unit. I'm curious to find out. I don't see this thing on a slab. That's kind of interesting. Okay, in this illustration, notice that there's quite a few changes that was made to this outdoor condensing unit in order to make this system viable. You'll find this illustration, by the way, on page 1347 of your textbook. And what it is, the insulated supply return lines routed to the retrofitted air conditioner. The lines are interrupted, rerouted to the loop field in the heating mode. The reversing valve routes the refrigerant to the loop field. In the cooling mode, the refrigerant is routed to the existing air coil assembly. There's a lot of piping here, guys. So I would say if you get a leak, it's going to be a real pain in the you know what to fix. Hopefully that's a biflow dryer. Okay, Mammoth water coil selection guide. They taught this is the problem with utilizing earth loop, utilizing H2O as a water source to remove heat. One of the issues that we have to face when we're utilizing this type of equipment is we can have biological growth, we can have scaling that takes place, and we have to have treatment options available in order to keep these systems functional. If anybody believes that you can circulate water forever and ever without inducing some problems, you got some issues. By the way, this is found on page 1329 On the lower left-hand side of the page, it's figure 44.6, selection guide for determining whether copper or cupronickel heat exchanger should be used. So based on your water contamination, you will choose either copper or you'll use cupronickel. Cupronickel has a higher resistance to corrosion all the way up to seawater, whereas copper does not. So if you want the better material, cupronickel is the way to go by far. Now, is cupronickel cheap? The answer is no. You will pay for it, trust me. Okay, in this illustration, which I think we talked about in the PowerPoint previous to this, we have a situation here where we are on page 1330, figure 44.8. Basically, the heat which came from the house is being rejected from the circulating fluid to the ground loop to the ground. In this illustration right here, this is also found on page 1330 of your textbook. Now we have a what they call a 4-pipe horizontal ground loop here. So this is a 4-pipe system. So you've got 4 loops here, A, B, C, and D. Talked about this previously in the PowerPoint presentation, but we'll just refresh your memory here. If you take a look at this particular illustration right here, this is going to be 44.21 on page 1337. And basically, this is a return well system for where you have a supply and return. So basically, you bring the cold water in, go through the pressure tank, go through the heat pump, and of course, the heat that was picked up is rejected here, and eventually this water will cool down. In theory, of course. Okay, in this illustration here, we have a heat pump here, and notice that we have the what appears to be the domestic hot water loop. And let me just verify and make sure if we're utilizing the waste heat off of this unit in order to heat the domestic hot water. I think we are, but I need to verify this. So give me 1 minute so I can verify that. Okay, in this operation here, this is going to be a this will be a closed loop water source heat pump in the heating mode. Okay, down below here, and notice that we have a hot water loop as well. We got the compressor, got the pump, we got the reversing valve. This appears to be a 4-way reversing valve, and of course you've got your cool supply air here. You have your earth source, basically your loop to the outside in order to reject the heat. Okay, in this illustration here, this will also be found on the same page 1332. This is a closed loop water source heat pump in the cooling mode. And the one previous to this was the heating mode. So here we are rejecting, putting heat into the building. Previously, let's go back one. This was cooling. So please see the difference. They're both on the same page, 1332. Okay, how about the pond or lake? If you're lucky enough to have a property that is on a pond or a lake, can that be utilized with a loop system for heating and cooling your house or building? Sure, it can. For you guys are not aware, if you've been to the Bellagio in Las Vegas, Nevada, all those fountains in the front of the hotel actually serve a function. They're not there just to impress you with the water flowing in and out. They basically are a cooling tower to remove the heat from the inside of the building, and the heat is rejected outside in those what appears to be fountains of water shooting all over the place. Just a nice tidbit of information. One of the problems that they have up there in Las Vegas, I don't know anybody that works up there personally, is they've got issues with hard water. I'm not surprised because the water probably is Colorado River water, which is full of minerals, and they have to be, when the water is used over and over again, basically, unless you add chemicals or do something with that water, you're going to have issues with it, okay? And those issues will basically cause the heat exchangers to scale up and cause problems down the road. So that being said, problems do exist with that water coming out of the fountains at the Bellagio in Las Vegas, in case you ever happen to get up there. And I'm not sure those things are still operating in this drought environment that we are going through at this point. But basically, we can utilize the lake to reject the heat for this geothermal heat pump system. So this is one method right here. Okay, here's another method where we're going to do the same thing, but we're going to use a direct burial method here in this particular case. Once again, if you're going to do geothermal, you have to have real estate. Bottom line, if you don't have real estate, no can do. So it might be problematic trying to do it if you don't have the available land in order to make this thing work. You'll find this illustration, by the way, on page 1330. This would be figure 44, excuse me, 44.12, and this will be a Slinky groundwater loop. Remember the Slinkies? Okay, here we have a situation where you're using a well, the water entering the heat pump at 55 degrees. You got the pressure tank, and then of course you got the machinery here. You got the duct air handler, ductwork for the house, the thermostat up here, a slow closing solenoid valve, and a condensate drain. So you'll have an evaporator coil inside that blower cabinet. Nothing mystical about this. The only thing that makes this different is the fact that we're utilizing a water source. In this case, we're utilizing a lake, stream, pond, or marsh discharge in the open loop heat pump in the heating mode. So this is going to be what you're going to see in the heating mode here. Okay, in this illustration, we show another heat pump system, and we show you the different parts of this heat pump. I want to verify where you can find this chart inside your book prior to going over it. And I believe this is going to be found on page 1350, and this is going to show the system schematic in the heating mode. Okay, notice that you have a four-way reversing valve up here. And notice we are in the heating mode. We have the earth loop, which is the evaporator. We have the liquid flow control, LFC. We have the air handler, the blower, the condenser coil, the active charge control that maintains the proper amount of refrigerant inside the system, the compressor, the outlet, which goes to the four-way valve. Remember, this is in the heating mode at this point. Okay, in this one here, this is in the cooling mode, so it's a little bit different. Now the earth loop is the condenser, and if you remember in the previous slide, that was the evaporator. So, so now we just changed the function. Okay, and then of course got the liquid line, got the vapor line, the compressor, the outlet, the active charge control for this unit, and of course the reversing valve and the evaporator coil with the blower and all the other good components there. Okay, this illustration is also on page 1350. This is the earth loop showing the heat being transferred from the earth to the phase changing evaporator refrigerant. And this is basically the ground here. The heat flows from the earth to the refrigerant because basically refrigerant vapor here is warmer and the ground is actually cooler. Okay, in the cooling mode, on page 1351, figure 44.51, the earth loop showing the heat being transferred to the earth from the base changing condensing refrigerant. So in this case, we're radiating heat out into the surrounding dirt. Okay, here we have an interesting illustration here. This is found on page 1352 of your textbook. And this is liquid flow control for your geothermal heat pump system. And the advantage is it coordinates with the condenser to set the proper rate of refrigerant flow for the entire system. So it's variable, prevents vapor from blowing through the condenser, ensures zero subcooling so that all the condenser is active, not just a part of it. Reduces compressor power requirements as a result of lower discharge pressure. Okay, and the next page on page 1353, this is basically an active charge control system. You're utilizing the advantages are prevents the liquid or unevaporated refrigerant from reaching the compressor. Remember, compressors are not designed to pump liquid refrigerant. Evaporates or traps refrigerant as necessary to keep the system properly charged and balanced in the evaporator. It's a flooded type to prevent buildup of superheat at the compressor inlet. Increases suction pressure by eliminating superheat. Interesting. Improves the volumetric efficiency of the compressor. Continuously allows the passage of compressor oil entrained in the refrigerant. Provides a means for quickly and easily determining whether the system is properly charged. Allows the compressor to run cooler. Reduces the compressor power requirement as a result of increased suction pressure. And of course, here's the illustration showing how this thing works, where the liquid vapor comes in, vapor oil mixture to the compressor. We have the liquid water vapor outlet, droplets, inner housing. Of course, here's our liquid vapor mixture inside here. This is liquid refrigerant here. And here's those sight glasses, okay? This can actually tell you what the level of the refrigerant is during the various part of the operation. You'll have a lower level of refrigerant if you have a higher heat load. If you have a low heat load, you will expect to see more refrigerant in this receiver. Okay, in this illustration here, I believe this is in the service sector. Hold on one second. I've never seen this here a minute ago. We are doing okay, this is found on page 1342. This would be figure 44.29. This is a hookup from the ground loop to the heat pump. And down below is the pressure and temperature sensing adapters for ground loop access. So these are tools that you would use for accessing to check the water pressure as well as the thermometer, the temperature. And these are devices that you have. Notice that you got a 1-inch hose bar, backup ring, and you have a PEETS port where you have the ability to read the pressure. It has a self-sealing part so the water can't blow out. And of course, you have the ability to measure the temperature. And here, these are your access points on this ground loop heat pump system, the circulation pump. So you have the ability to check the flow rates by these devices, which are hooked up when the system's put in and commissioned. If you don't have these PEETS plugs, as an example, you're going to have a lot of trouble troubleshooting this system, and you're going to have to add these components later on. I have not directly worked on this type of system. I have seen one or two of these around, but not necessarily in the SoCal area. I'd say probably more in the Midwest and the East Coast than out here, where people tend to have a little bit more real estate in order to make these things work. Okay, in this illustration right here, we have a gas furnace, and then we have a air conditioner, And this basically is an illustration on page 1345. This is a cooling mode schematic showing how this unit works here. Basically controls the font for make sure that we have enough refrigerant flowing. So basically this is a large reservoir. You have your 3 sight glasses. Here you have the air conditioner, the traditional outside condensing coil. And of course you got the evaporator coil up here, the metering device. And then we have the ground loop. The refrigerant earth ground loop is not used for cooling in this application. Now in this application, cooled liquid refrigerant sent to the refrigerant loop to be warm. So in this case, we are using the ground loop. In the previous slide, we were not. And basically, the cool liquid refrigerant sent to the air coil will provide, obviously, to absorb heat in the evaporator coil from the return air or to cool the house down. Hot compressed gas is sent to the outside air coil to reject the heat. And of course, in the heating mode, we have a different situation here. We've got a reversing valve. Notice that you've got one common port, and then of course you have the selector ports here between the top and the bottom. And warm refrigerant liquid gas is sent through the accumulator to the compressor. Once again, the compressor is only designed to pump refrigerant vapor. And I believe that is the end of this presentation.